Well, it's time for us to do some practice with problems which involve derivatives of trig functions. Ah, good stuff. It's great. Trig functions are beautiful. And make sure you're getting that practice in, which means doing as much as you can on your own. So make use of that pause button. You should be watching these videos to get different perspectives and to help you get unstuck. And so as you're working through the problems, once you say, aha, I see what to do, pause and do it. Do it. And then you're going to be great because, of course, you're a wonderful person. All right, let's get going. So our first problem, find the tangent line to y equals 6 tangent of x minus root 2 secant of x at x equals 1/4 pi. Of course, I don't know why they chose to parenthesis around that x, not that x. Well, we're equal opportunity parenthesis users, so we'll put a parenthesis there. All right, so tangent line. Okay, so we know tangent line. We're like, all right, we need to get a point, and we need to get a slope. So this shouldn't be so bad. So what do? Well, we know our x-coordinate, that's pi over 4, comma, and now we need our y-coordinate. So our y-coordinate would be 6 tangent pi over 4 minus root 2 times secant of pi over 4. Now, tangent of pi over 4, this is a nice value for tangent. Do you remember? So tangent of pi over 4 is 1. So that's going to make that value nice. How about secant of pi over 4? Now you might not know this off the top of your head, but maybe we can reason it out. Now, secant is related to cosine. So 1 over cosine is secant. So if we can figure out what cosine of pi over 4 is, then we're good to go. Well, cosine of pi over 4 is oftentimes written as root 2 over 2. Another way to write cosine of pi over 4 is 1 over root 2. So if you flip it, then you get that secant of pi over 4 is root 2. So what do we have? We have 6 times 1 minus root 2 times root 2. Well, that becomes 6 minus 2, which is 4. Good. Now, next up, our slope. So, of course, slope means derivative. So we start by taking our derivative and see what happens. So derivative 6, derivative of tangent is secant squared. Then root 2 is a constant, and the derivative of secant is secant tangent. All right, there we go. There's our derivative. Now, plug in pi fourths. So we can do like a little evaluation sign if we want. Or we could do y prime parenthesis pi fourths, whatever makes you comfortable. So what would that be? 6 secant squared of pi fourths minus root 2 times secant of pi fourths times tangent of pi fourths. But we know these values because we've talked about them. See, like the secant of pi fourths is root 2, tangent of pi fourths is 1. Secant squared of pi fourths, well, root 2 times root 2 is 2. So what do we have? Well, we have 12 minus 2, because you get a root 2 times a root 2, also known as 10. So our slope is 10. Now we have our point, we have our slope. So y minus our y value, which is 4, is equal to our slope 10 times x minus our x value, pi over 4. And that's our line. We found it. Woohoo! Good. Nice. Nice. All right. Well, let's do another problem. Ooh, more practice with taking derivatives. Okay, so we're going to find the third derivative of tangent and the second derivative of secant. All right, well, let's begin with the third derivative of tangent. All right, so let's see. So we'll start, our function is tangent. Well, let's find our first derivative, because if we're going to find the third derivative, I mean, it's 3 derivatives, so we always start with the first one. All right, so the derivative of tangent, we just know that off the top of our head. That's our secant squared theta. Now, what's our derivative of secant squared theta? So what are we doing? We're really taking the derivative and plugging it in. So it's the derivative of the derivative. Now, this is the same as the derivative of secant theta times secant theta, because we can do that. And what do we do? Well, that's a product rule. So that'll be the first, which is secant theta, times the root of the second, which is secant theta tangent theta, plus the root of the first times the second. Yeah, I went in a different order than I normally do. But the important thing is everybody got their turn. You know, it's important. Everybody gets a turn when we're taking derivatives. So these are actually the same thing. So it becomes 2 secant squared tangent theta. Okay, all right, nice. Now, that's the second derivative. See, it was the derivative of the derivative. So, one more layer to go. So we're going to take the derivative of 2 secant squared theta tangent theta. Okay, see, now we're plugging our derivative back into our derivative machine. All right, so we'll do it 2. Do we know the derivative of secant squared? Yeah, we just did it. See, there's the derivative of secant squared. So 2 secant squared theta tangent theta. Then, so see, the 2 is a constant, derivative of the first times the second, plus the 2 is a constant, the first times the derivative of the second, and derivative of tangent is secant squared. So, what do we end up with? We end up with 4 secant squared theta tangent theta plus 4 secant, tangent squared, because these two tangents multiply, plus 4 secant to the 4th theta. All right, there's our beautiful answer. Now, could we rewrite this? I suspect we could. Are we going to? I suspect we won't. Well, the reason why I say I suspect we won't is there's so many ways to rewrite things which involve trig functions, and there's lots of beautiful identities, and it's not clear what advantage there is to rewriting. See, we want to simplify not for sake of simplifying. We want to simplify for a reason, and oftentimes that reason is because I need to do something with the answer. But if I got an answer, it's like, well, this is the answer. Why do I need to simplify? So we'll stop there. Okay, so this is the first piece, right? Our third derivative of tangent. Now, that's only half the problem. So let's do the other half. Okay, so we start, we're saying, well, the derivative of secant theta, we know what that is. That's secant theta tangent theta. That's our rule. So if I want to take the second derivative of secant, what do? Well, I'm going to plug secant theta tangent theta into our derivative operation. Okay, so I'm taking the derivative of the derivative. And so now we're going to do a product rule. Derivative of the first, derivative of secant, is secant tangent times the second. See, the derivative of the first times the second plus the first, which is secant, times the derivative of the second. So the derivative of tangent is secant squared theta. All right, we barely fit it on the screen, but we got it. So that becomes, there's a secant theta tangent squared theta plus secant cubed theta. All right, there's an answer. Now, could we simplify? Again, yeah, it's possible. But right now, it's not clear that there's a motivation to simplify. So we'll just leave it in that form. And yes, there are other ways to write the answer. Almost always whenever you're doing a problem in trigonometry, if the question is, could you rewrite it? The answer is, yes, you could. But we really want to have a motivation about why we would want to before we do the work. All right. So there we go. That one's done. All right. Next problem. This is nice. It's just nothing too fancy here. We're going to find a derivative. And we can see that this is an expression, involves sort of two aspects. We've got our trig functions, the sine and the cosine. We've got some algebra showing up as polynomials, x squared and 2x. And boy, this is probably going to get to be like a huge, massive expression by the time we're done. Well, one way to find out. So what do we do? Well, we're going to go through it piece by piece. Now, the first part, x squared sine of x, that's a product. So we'll do a product rule. The derivative of the first, 2x times the second, sine x plus the first, x squared, times the derivative of the second, cosine x. Then we go, okay, that's our first piece. So that's where that came from. And then we're going to go to our next part, plus, okay, now what do we have? Derivative of the first, and 2 as the constant, so everything's going to have a 2, so I can think of it as really the x, so it'll be 2 cosine x. All right, plus 2x times the derivative of cosine, which is negative sine. All right, so that's our second piece. And not to be forgotten is our last piece, the derivative minus 2 times sine. Well, minus 2 is the constant, derivative of sine is cosine. And we say, okay, well, there's our derivative. But in good faith, we should at least do a quick glance to see, does anything simplify? And you're probably like, well, yeah, you just talked about not simplifying. Look, there are certain things that you should do. Look for cancellation. If you can cancel, you should cancel. If you can add 6 plus 4, you should add 6 plus 4. Because I think they asked us to do this for a reason. I suspect something is about to happen. See, as I was writing down, I said, hey, that minus 2 cosine x, that looks like that plus 2 cosine x, so those cancel. There's a 2x sine x. Here's a minus 2x sine x, so those cancel. So what you're left with is x squared cosine of x. And that's the answer. See, it was this long expression at the beginning, but then it collapsed. And that's kind of an interesting idea. Sometimes a complicated function can have a beautiful derivative. And, of course, sometimes a beautiful function may have a complicated derivative. You never know. That's why you need to do the work. Do the work. All right. Let's try another one. So, if the spring has position s of t equals e to the minus t sine t, find acceleration. So what's happening here is you have a spring. So you should think of it as moving up and down. So this is really, the spring is attached up here, and it's just do, 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 do. Now, what's happening when you see e to the minus t sine t? Now, in a perfect spring, it will just keep oscillating forever. Up and down and up and down and up and down and up and down. So when you look at a spring of that form, what you see is if you look at the height over time, it follows this nice sinusoidal pattern. But of course, nothing is in a perfect environment. So what tends to happen over time is that it starts out, but then it starts to slow down. And of course, usually not that quickly, unless maybe you're like shocks on a car, you want that to slow down pretty quickly. So it starts to oscillate, but not quite as much. It dampens over time. So in essence, what we are encountering here is like this is a spring that's experiencing some kind of dampening effect. So what we're really seeing here, here's our axes, what we're going to see is over time, it's going to get closer and closer to the axes, right? It's shallower and shallower heights. So that's the type of behavior that we're seeing. So this is modeling. Again, you'll see this in differential equations. This is kind of a dampened spring going on. But okay, so that's the idea of the problem. Now, what do we really need to do? Well, really, there's not that much work to be done here because we have a position. We're after acceleration. And so if I want to go from position to acceleration, what do? Is I go through step by step and take two derivatives. Now, we have taken the derivative of e to the minus t. That was in some practice that we did before. So as a reminder, what is the derivative of e to the minus t? It is, you put a minus in front, so it's minus e to the minus t. So here we go, s prime of t. So the root of the first minus e to the minus t times the second plus the first e to the minus t times the root of the second, which is cosine t. So product rule. Now, one more layer. The second derivative. What will happen? Well, if you look at the second derivative, what you'll see is okay, the root of the first, another minus comes down, so it's really e to the minus t, and then times the second, and then, all right, plus the first, which is minus e to the minus t, times the root of the second, which is cosine t. All right, add to that the root of the first, minus e to the minus t, times the second, plus the first, e to the minus t, times the root of the second, which is minus sine t. Now, we can do some things here. What can we do? Well, what do you notice? Well, there's two things. First off, if you look at the first and the last terms, they are going to cancel out. So that's nice. If you look at the middle terms, they combine. So what you get is you get minus 2 e to the minus t times cosine t. All right, good. Well, I have a minute or two. I'm just going to wax poetic for a second. And if you think about a normal spring, so this is the position. Suppose my normal spring is modeled by just the sine t. There was no e to the minus t. What's the second derivative of sine? Do you remember that? We did that. So the second derivative of sine is negative sine. So what ends up happening is that the acceleration goes exactly opposite to the current location. And if you're familiar with something called Hooke's law, that's reflected in Hooke's law. See, Hooke's law says the acceleration, which really deals with the force, is proportional to the distance, which means that the acceleration has something to do with how far off you are away from the center. And therefore, if you're at the center, which is the natural resting point, then there's no acceleration acting on you. But if I pull you down, if I stretch the spring, then there's a lot of acceleration pulling it back up, exactly opposite to where it currently is. Now, take this function here, e to the minus t sine t. You'll notice it's not just the negative of where you started. See, there's this sort of a shift happening. It's out of phase. Sine t became cosine t. So what happens is it's not exactly pulling exactly from proportional to where you're at. And because of that out of phase alignment, that's why you get to experience a dampening effect. All right, okay, that was somewhat philosophical. Not really relevant to the problem. It's just fun to wax poetic when you're doing these problems. Okay, so that's the answer there. Good. All right, let's try another problem. All right, here we go. Consider the functions f of x equals 2 tangent of x plus 2 secant x, and g of x equals tangent of x plus secant of x quantity squared plus 1. Now, is g of x the derivative of f of x, or is f of x the derivative of g of x? Justify your answer. It might be the case that you are a well-versed person in calculus lore, and you know something which we haven't talked about yet called the chain rule. So let's suppose you knew about that. And if you saw this problem, you'd be like, wow, this is so obvious what the answer is. I can spot it. It's because when you do the chain rule, when we take the derivative of g of x, you would bring the 2 down, and then you have 2 times tangent plus secant, which is exactly what we see there. And we're done, and life is good, and woo, we move on. Easy peasy. Keep going forward. All right. But it's not right. Here, so you got to be careful. These are not just randomly chosen functions. It's easy to look at this and say, oh, if you're not careful with your rules, and of course we do want to learn to be careful with our rules, if we take the derivative of g, it might look like the derivative of f, but that's not quite true. All right, so let's start by taking the derivative of f and see what happens. So f of x is 2 tangent of x plus 2 secant x. So what is f prime of x? Well, that is what? Derivative of tangent is secant squared. Derivative of secant is secant tangent. All right. Now, let's compare it to g of x. So what do we know about g of x? Well, it's tangent of x plus secant of x squared plus 1. Let's actually square that out and see what happens. So, if you square this out, that would be tangent squared x plus 2 tangent x secant of x plus secant squared of x plus 1. Now, what we do is we can do a quick comparison. And we glance at this and we say, yeah, they're not the same. But then we remember something. Trigonometry can be tricky. And things that look different might actually be equal. So let's be a little bit more cautious. We say, well, certainly it's the case that we have a 2 tangent of x and a secant x, and here's a 2 secant x tangent x. Those have to be the same. I see a secant squared x, and there's 2 secant squared x. So let's actually break this apart. So let's write this as secant squared x plus secant squared x plus 2 secant x tangent x. And then we can say, all right, so we already accounted for that 2 secant x tangent x. Here's a secant squared x. Here's a secant squared x. How about tangent squared x plus 1 and secant squared x? Are those the same? And now we say, I know an identity. There's a cool identity, and it's the following. We'll start with the one you're probably more familiar with. Sine squared plus cosine squared equals 1. All right, I think we all know that one. Now divide through everything by sine squared. Sorry, cosine squared. Cosine squared. Cosine squared. Cosine squared. And what do we get? Sine over cosine makes tangent squared. Cosine squared over cosine squared, 1. 1 over cosine squared is secant squared. So, tangent squared plus 1 is secant squared. Exactly what we need. So these are the same. So, even though it may not look like it, especially as I said, if you know the chain rule, it turns out that we can say that the derivative of 2 tangent x plus 2 secant x is equal to tangent of x plus secant of x squared plus 1. So, be careful. Be careful. Now, it's good practice, and I'm not going to carry it out, but take the derivative of tangent of x plus secant of x quantity squared plus 1 and see what you get. And you can check by plugging in some points and some values, and you'll see that what you get is not 2 tangent of x plus 2 secant of x. So, well, you got to do the work. You got to do the work. All right, good. And that brings us to one final problem. Of course, the last problems are always the fun ones. So, the half angle formula for tangent is that tangent of a half x is 1 minus cosine x over sine of x. And so we're going to find the derivative of tangent of x over 2. Okay, so that's our first thing. And then it says, hey, you know, there's this derivative of tangent of x. Let's make a comparison. So as a result, I should say as a result. Let's recall the result that the derivative of tangent of x is secant squared of x. So we are suspicious that when we work that expression, we should get a secant squared out. All right, fingers crossed if we get secant squared. it's something beautiful in math has happened. And if we don't, well, math is more mysterious. Okay, so let's begin. So we know that the derivative of tangent of x over 2 is like, well, I don't know how to handle that, but I don't have to handle that directly because I can say this is really 1 minus cosine of x over sine of x. And see, the nice thing is I know how to handle things like cosine of x and sine of x because I know those rules. And this expression, 1 minus cosine x over sine of x, that's a quotient. I have a rule for that. So we're going to take our rules. We're going to take the bottom, which is sine of x, times the derivative of the top. Well, we have 0 minus, the derivative of cosine is negative sine. Minus, say, so low d high, minus the top, high, times the derivative of the bottom. The derivative of the bottom is cosine x. All of that divided by the bottom squared. Okay, so far, so good. So let's clean it up because we want to try to understand what is this in comparison to the derivative of tangent. So we want to get a better grasp of what we're dealing with. So we have a minus, so we can make that into a plus. So what do we have? We have sine squared x upstairs in the first part. Then we have minus cosine of x. Okay, minus makes a plus. Cosine squared of x. And that's over sine squared of x. All right, well, sine squared x plus cosine squared x is 1 minus cosine of x. Now, sine squared of x, 1 minus cosine of x, oftentimes when I see 1 minus cosine x in the back of my head, it's like, there's like 1 minus cosine squared is really convenient when we have 1 minus cosine. And sine squared of x turns out is equal to 1 minus cosine squared. It's one of our nice identities. So I'm going to replace the sine squared by 1 minus cosine squared. Now, why do I say it's nice? Because I can write the top 1 minus cosine, and the bottom, this 1 is really 1 squared. So it's a difference of squares. So it's 1 minus cosine, 1 plus cosine. Ah, nice. So we can cancel the 1 minus cosines, and we're left with 1 over 1 plus cosine x. Cool, cool. That's a beautiful derivative. Now, does that look anything like secant? No, it doesn't, does it? Huh? Well, now we start pondering. Maybe there is no connection, but it feels like there should be. So, here's where we're going to do a little bit of interesting manipulation. All right, here's an idea. You see, I suspect I started with an x over 2 on the inside of this expression. Maybe I should get back to having x over 2 on the inside. So let's see if we can do something. So this would be 1 over 1 plus cosine of 2 times x over 2. Okay, that's certainly a true statement, but you're like, okay, you haven't done anything, Steve. You just put a bunch of 2's on the inside which cancel. But now we start rummaging through our catalog of trig identities. And the nice thing is there's only like 6 that we really need to know. And one of them looks vaguely like this. So we've talked about some of our trig identities that we need to know already. And so let me talk about the ones we haven't talked about yet. So there's something called power reduction. And the idea is reducing, if you have like cosine squared, it's like, I don't like the square. I want that to be a lower power. That's how power reduction works. But it works both ways. So anyways, what's true? What's true is that cosine squared of x is 1 plus cosine. I shouldn't have used x, but, well, I've already gone down that rabbit hole, over 2. And sine squared of x is 1 minus cosine of 2x over 2. So, do you see how I have 1 plus cosine of 2 something? So, this says 1 plus cosine of 2 something. Ignore the fact that it's an x. That's going to distract us. So, I'm going to go ahead and rewrite it that. I can already tell that I'm going to get confused if I don't rewrite that. So, here's the rewriting. 1 plus cosine of 2 times something. So, something is a box. All right, so 1 plus cosine 2 something, if I move this across, is equal to 2 cosine squared of something. So that's our identity. And the reason we like this identity, by the way, is we almost always use it going from cosine squared over to this expression because we like to reduce the exponents. They can be hard to work with. But identities are a two-way street. If A equals B, B equals A. So we can use them whichever way is convenient. So in our case, and really in all cases, when we're dealing with this, the question becomes, what's in the box? What's in the box? What's in our box? It's this thing, the x over 2. All right, so here we go. So this becomes what? This is equal to 1, well, let me just put that to the side here, 1 over 2 cosine squared of x over 2. And now you're like, hey, I see what that is. See, that 1 over 2 is like a half. 1 over cosine squared is like secant squared. In fact, not only is it like secant squared, I'm going to go ahead and put it over here, it is secant squared. So we can say that the derivative of tangent of x over 2 is 1/2 secant squared of x over 2. And that's our answer. Wow. Now, it is, of course, also equal to 1 over 1 plus cosine of x. But when we write it in this expression, now we start to see the connection. Hey, there's this nice, beautiful relationship. Because when I took the derivative of tangent, I would normally get secant squared. I'm still getting secant squared. And the insides are still the same. Somehow there's a half showing up. My goodness. If we had a nice way to understand why there was a half showing up right there, I tell you, that would really change the game. All right. Well, you know where we're going because we're going to figure that out. But that's for another session. But thank you for hanging in there with the practice. Keep doing it. You're doing great. And I hope you have a good day.